Okay, good news. This is the last presentation, and for those of you who have remained so long, I'll try to make it fun for you. This is going to be about performance optimization, since not so much about performance optimization, but about the sense of performance optimization. But first of all, a couple of words about myself. For those of you who don't know me, my name is Aliaksandr Valialkin. My nick is Valiala. You've probably seen me on GitHub or on Google. I'm an author of Go libraries such as FastHTTP, FastJSON, Quick Template, and others. These are optimized for performance. Well, of course, I'm a big fan of performance optimization, and I have been working on my own time series database, VictoriaMetrics, so I encourage you to use it. All right. Let's talk about when we need performance optimization. Several use cases. First, when your program is slow and you want to optimize it. The second situation when you need it is when your program hogs a lot of hardware resources and you want to cut costs on IT infrastructure or on your hosting. And another popular use case, I believe perhaps it's not a very good case, but many people kind of abuse it, especially in the former Soviet Union, benchmark games. I don't know, even I do that. We like to optimize our programs in order to show good results on benchmarks, and these results do not necessarily reflect the real production performance. Of course, performance optimization does not always improve your program performance overall. It comes at a cost, and this cost can be too high for this performance optimization to proceed. And in my presentation, I'd like to focus on examples from real projects such as FastHTTP, FastJSON, VictoriaMetrics, standard Go packages, and the last example that has nothing to do with Go, CPUs. Perhaps you've already guessed what that means, but don't tell anyone just yet. Let's start with FastHTTP. So FastHTTP, if you don't know what that is, raise your hand. Okay, so I don't have to explain to you what that is. All right. Tell the uninitiated later what that is. So anyway, this is the extension of the standard net HTTP package, but one that's optimized for performance. FastHTTP handles response buffering, different HTTP headers parsing, using slices instead of maps for key-to-value entries, request CTX reuse, and the DNS caching. Let's consider response buffering first. That's how standard HTTP protocol flow looks if you write it in Go. Oh, by the way, this is not Go, that's just a snippet, a pseudocode snippet. We get a connection function. This function gets an HTTP request, checks if it's closed or not. If it's closed, we exit the function. If it doesn't, we send the response to the connection. And we do this in a loop, because the connection can have the keep alive flag on. What is bad about this code? Well, the bad thing about this code is that for every request, for every response, it should read and write with a connection, and that's not good. To fix that, we do something like this. This is a function that's optimized for HTTP pipelining. If you don't know what HTTP pipelining is, when you send several requests via HTTP, we can do so without waiting for the answer from the server. That's how this optimized function looks. So we wrap the connections we would route them to the buffers, not readers, not writers, and then in a loop we read the request from the buffered connection. If it's closed, we flush everything we have in our write buffer, and then we exit the function. Well, this slide shows everything you saw on the previous slide. Here we buffer everything and we process things in the buffer. And after this, what does this thing do? It checks whether the buffer has some data, I mean the read buffer that receives the request. If this buffer is empty, we need to flush the responses that have accumulated in the write buffer. What do we get? What's in it for us? It decreases the number of system calls for read and write in the use of
bufferization. The buffer by default is 4 kilobytes, so neither the reader nor writer can do differently. So at every read from connection that's wrapped in new reader, the reader tries to read 4 kilobytes of data, up to 4 kilobytes of data, and put them in the buffer. And within these 4 kilobytes, you may have more than one query. And so using one syscall, we get several requests and process them in the cycle. Same thing applies to the response. Right. The bufferized network connection doesn't, well, the data is not written immediately there. It's written in the 4K buffer. And in order for the data to get into the connection and further on to the client, you need to call the flash function. Here it is. And this also helps us save on the number of system calls required to send the response to the client. So this is the advantage of this thing. But there are also drawbacks. The sins, as I have named them in the title of my presentation. And the sins are like this. Sin number 1, so that the HTTP pipeline is prone to head-of-line blocking, which actually means that if we have sent several requests to the HTTP connection, and if the first request takes a lot of time to execute, then all other requests after it will be waiting until the execution of the first request is finished, even if they can be processed much faster. This increases our latency for the next request. And the other drawback is that HTTP pipelining is rarely used in real life. For instance, all modern browsers, even though do support HTTP pipelining, it's always disabled there. Why? Because most servers, most HTTP servers that were popular in the beginning of the 2000s, in the middle, either didn't support HTTP pipelining or had implementation errors. So It just historically happened so that it's always been disabled. And now the new HTTP2 protocol, so all browsers just enabled HTTP 2.0. The biggest drawback of HTTP pipelining optimization is that, and I avow, I made it to cheat the benchmark decompiler by the factor of 2. Let me explain what TechEmpower benchmark is. It's a benchmark that checks the speed of different HTTP servers for different types of calls. And there's a call type called plain text. So where you just send 16 pipeline requests and you wait for the response, like something like hello world from the server. And so for this plain text benchmark, this HTTP pipelining optimization allowed to speed up the HTTP library of the server twice. They recently hacked this, and you had to initiate a bug about that. You can use this link to see how it has been fixed. The next example, deferred HTTP header parsing. Fast HTTP doesn't parse the HTTP headers immediately in the server request. It's just looking for the marker of the HTTP header and its two carriage returns, and puts unparsed headers in byte slice locally. And this byte slice is only parsed as the first at the first call to the HTTP header. So this code example for fast HTTP, where the HTTP header will not be parsed at all. This code just writes hello world in the response string and doesn't read the headers. And this is the code that does read the headers, and we can see here that as the header is read, the HTTP server passed HTTP headers, spending resource on that. So what are the benefits of this implementation? It's clear that it's going to that HTTP server will run fast without HTTP header calls for each request. The drawbacks of this schematic, the sins, are that in real life the HTTP headers usually do read such headers. And this optimization only shows its advantage in benchmarks like plain text benchmarks, where code, well, this is the way code looks, just like here. You just send responses and that's it. So the usage of slices instead of maps. Fast HTTP uses key-value slices instead of standard Go maps, bitmaps, in order to store the list of query arguments, query args. I don't know how to put it in Russian. I forgot my Russian. So the list of headers and the list of cookies. Let's now see how it's implemented first. An example of implementation. So we have this structure, key value, with two fields, 2 byte slices, and we call it slice map. This is the way we add an item into the slice map. What do we do here? Well, we keep it in or save it into the temporary variable KVS, and then we check if there's room left for any additional information. And if its capacity is higher than its length, then this room is there. So we just add or increase the length of this byte slice map, and this helps us save on the memory allocation. Otherwise, if unless we have an additional element in the slice, we add it. And then we call this element, call this item, and write there the key and the value for the byte slice. You see, we use this kind of notation, comma 0, which means that we're reusing the memory that's already been allocated for these variables, key and value. So this kind of coding allows us reusing both the slice map items and also each key and value in each of the byte slice, saving on memory. So this is the way data reading is implemented from byte slice. So we just go through all the slice map elements. It returns the key. If the key matches what we have, then we use this value. So what are the benefits of this method? Because in the usual conditions, the elements where the slice map are used include headers, query args, and cookies. Usually their number is not too high, not more than a few dozen. And for such numbers, slice maps run faster than standard Go maps. And just like I've shown in the previous slide, slice maps allow reusing memory as opposed to usual maps. So we can use the same slice map many times and thus save on memory allocation. And there's another feature that is sometimes needed, is to keep the original order of items that we got in our requests. So, for instance, you've got query args in a certain order. They will be kept in the slice map in exactly the same order, as opposed to the usual maps where this order will be random. But there are issues about this method. If the number of query args or the headers is too large, then, as we've seen from this slide, the reading of data from the slice map is an OTN operation. So you need to go through all the slice items, and this can happen very slowly. For instance, if you're talking a slice map containing thousands or millions of elements, just imagine your query args containing that many elements. Another drawback is that slice map is prone to fragmentation. If you keep or save some large value in the slice map, let's say a megabyte large key or value, then after that the slice map will always take this megabyte, even if you replace that value by small ones. And the last drawback here is that the value returned from slice map belongs to the slice map and therefore becomes invalid after the slice map has been used. And you have to remember that. The next example is about the request CTX reuse. Request CTX is the main object replacing the standard HTTP response writes and HTTP response requests at the same time in fast HTTP. It's the only object that's passed to your request handler, and this object is reused by the HTTP server. This is how it looks. It's a pseudocode as well, but it's very similar to what you get. So we get from the pool request, and we then do a loop to read the request. It's put. So this is, by the way, is your request handler, and then we write in response connection, and we do it in a loop. So your request handler will be reusing this request CTX object and whatever is contained inside it at every call of to your request handler. What are the advantages? The advantages are that we're reusing request CTX. Therefore, memory allocation goes down, data locality improves, and the speed improves. But as to the drawbacks, I think you've already guessed what they are. So it's very easy to abuse this API. The most widespread case is when you take a certain object from this request CTX in your request handler and save it somewhere by link, or you use it in some routine that's running in parallel, or you pass it to a channel, so that this object, this link stays, is kept alive after the request comes back, which means that you get fast HTTP running wrongly, because all sorts of garbage will be kept to follow that link. Not what you've expected, a classic data race. And that's there's also another the same problem as in the previous case. It's about memory fragmentation. If your request CTX object gets some large response body or some other large object, then this large object, when the request CTX object reused next, will keep the memory. So even if you've deleted it, but the memory allocated to it or for it will still be used. You have to remember that. Another example, DNS caching. Fast HTTP has a client, not only the server. And for the client side, the DNS name resolving is used, host naming in IP. So fast HTTP has DNS caching for this to improve the speed. Fast HTTP caches this mapping between the host name and the IP address for a minute. This is the pseudocode showing how it looks. So we have some DNS cache here. We're checking path's name, if the record is there, and if it's there, and the time required for its storage is not larger than 1 minute, we return this path in the fast path. And when it comes to the slow path, we really resolve the host to IP and put it into the cache. But this is a pseudocode, of course. There are no locks here. It's all been written this way to simplify the slides. But it looks just very similar to what you see here. What are the advantages? We speed up DNS resolving. Drawbacks and sins are that this kind of caching breaks your HTTP clients. in environments where DNS changes often. It's a typical example of such environments is Kubernetes, where when pods are loaded, they can be moved between your nodes, therefore with different addresses. And after such a reload, your fast HTTP client will be trying to connect to the previous node, and you'll have to wait a minute until that cache expires. So we're done with HTTP, and now a couple of examples about the fastJSON library. The fastJSON library, again, comes to replace the standard JSON library, and it runs faster, but not always better. Let me tell you why. There are three drawbacks here, three sins. Memory reuse, fast string unescaping, and a custom parser for integers and floats. Let's start with the memory reuse. FastJSON contains the parser object that's used to parse JSON, and this parser object takes this data that you pass with this object. I mean, this data belongs to this parser object. Here we have an example. So we call the parser from the fastJSON, get some value, and this value actually belongs to the parser after this line. So this value is stored in the parser object, and when we read the full line, put it into B, this B string also recursively belongs to this parser via the object value. And so at this line, we're calling parse using this parser object. It's a different JSON. And so after the line, this V and B and all other objects that we received over V and P become invalid. That is, we get VV returned that already contains the parser structure, and all the rest becomes invalid. So what are the advantages of this approach? It's clear that the memory reuse allows save on memory allocation and speed up JSON parsing. But the drawbacks are about the same, just like with request fix. It's very difficult. It's an API that's very easy to abuse. Like in the previous example, if you keep saving links that you got from the parser after the parser has been used for a different JSON, these links become invalid. They will contain garbage. And the second drawback is that, again, and it looks like the previously listed drawbacks, this parser, with time, can bloat in size, take a lot of memory for the same reason that I've already discussed. So if you parse JSON objects of different configuration, where, for instance, initially the first item takes a megabyte, the second 1 byte, and then after that, using the same parser, you parse a JSON where these items swap places. This parser will allocate 2 megabytes. So 1 megabyte for the one that now contains 1 byte, and the same megabyte for the one that used to contain 1 byte and now contain 1 megabyte. Another example, fast string unescaping. In JSON, it works like this. We are looking for the escape symbol in the string. If there's no escape symbol, we just return this string. There's nothing to unescape. if only once one escape symbol has been found, we're calling a function that goes through all the bytes of this string and unescapes each item, every character in this line. The advantage of this approach is in that the lines don't containing unescaped symbols will be passed very fast, because this function, it's a standard Go function, it's speed optimized. The drawback of this method is that the escape symbol containing strings will be passed slowly, and the second one is that mixed lines with both having and not having escape system will, affect the performance, which is not acceptable always. The next drawback. This is an example of a parser, a custom parser for floating point and integers in fast JSON. So the advantage of this custom-built parser is that it runs faster than the standard one from the star.conv package. You can guess about its drawbacks. Well, the drawbacks are like this. So you immediately get this question: why string conf has been optimized for speed here? And the answer is that they can process edge cases that this custom parser can't. In edge cases, you usually spend a lot of resources to process your edge cases. What kind of cases do I mean? Large numbers. That's my parser can only work with small numbers. If it sees a large number, it just calls the strconf function. So with large numbers, it starts slower. It runs slower. Its second drawback is that it returns a 0 if a wrong number was supplied. And the third drawback is that it may work improperly for some corner cases that I haven't envisaged when writing the code. Okay, we're done with fast HTTP, and let's take a look at my favorite library for the database time series. Well, it's not a library, it's just database time series. We have several exciting examples. VictoriaMetrics can read data that you've got from Prometheus using the remote write IP protocol. And for this, it uses protobufers. Protobuf. Initially, we used a standard protobuf parser that we got during the standard code generation process from the Prometheus package. But as it turned out, the standard implementation allocates a lot of memory. And so we had to optimize this code manually, the one that had been generated by this code generator. An example, a couple of examples of modification. This is the way data structures look from this protobuf. There's time series that keeps a set of labels and samples. Each label contains a name and a value. Each sample has timestamp values, a timestamp value. A modification example. First, we had type, and the name field had the type string. I changed it to byte slice, and correspondingly, I changed one line in the code where you mention this name. It used to look like this, and so in The first line copying was happening from the data slice into the newly allocated memory. So in this line we used to have memory allocation. I replaced it by this line. I just took the string out of here, and just like as many of you have understood, there's a certain drawback about this line. I'll tell you about it later. The second case for modification was like this. I removed the pointers. Correspondingly, what I've changed, I added a new label element to this line that allocates a new label element in memory and adds it to the labels array. Looking at the code now, that is checking the array.
Increases the length of this array and reuses the element accordingly. The advantage of this approach is that I was able to decrease memory allocation down to 0 through the reuse of memory and increase the performance of parsing of protobuffer. The disadvantage of this method is that this is handwritten code and it's hard to very hard to maintain, because it was handwritten, and if you remember this example, remember I deleted the string transformation. It turns out that this data slice byte should be valid and should remain valid until we use, well, as long as we use this name. As soon as this byte becomes invalid, our name becomes invalid and it starts to store garbage, begins to store garbage. Now let's consider standard Go packages. I see that I'm running out of time, but let's go quick through this. Go quickly. We'll do two examples. First, we'll consider how pools can be used for small numbers. And I will also tell you a few words about syncpool. That's the function to format int from the standard Go library, Go package. It does the check of the int number so that it doesn't check the int, that it doesn't increase, that it doesn't exceed 199. And a base should be 10. We call this small function that returns a string from the global scope, name scope. I also added some. What's the benefit of this code? It is quick to transform numbers to string for numbers that are below 100. The drawback is that this code works to demonstrate some unexpected behavior if you have mixed numbers. When you profile your program, you see that it allocates 0 memory and then it begins to allocate memory just because you start to parse large numbers. Syncpool, I don't know. Okay, let me give you the one last example related to CPUs. Modern processors, modern CPUs perform actions based on instructions in a multi-level pipeline. This pipeline is broken when the processor finds an instruction of conditional jump. So the processor doesn't know what path to take out of these two things. So that slows down your program because the pipeline has to be run once again. processor developers found a way out of this situation by predicting this branching and speculative code execution. But it turned out, in fact, last year, this performance optimization does not come without a cost. It can even lead to meltdowns and Spectre-like vulnerabilities, which requires CPU runtime slowdown. Well, that's it. Thank you very much. Thank you very much. So, do we have any time for questions? Okay, there are two people that want to ask a question. I have a very quick question, very good presentation. And here is my question. Why do you do this for HTTP? To fool benchmarks? But what about other things? Okay, some metrics increase. Why did you sell your soul for a 10% performance increase? Well, usually we get a performance increase around 10, a little bit more, 10% or slightly more. If it doesn't give me anything on that level, then the performance increase is not worth it. Some parsers can achieve better performance increases, but there are very many other examples that give you a much bigger